Bismillahirrahmanirrahim. Now we will discuss today, this is second part of the Citral. This is natural products. We have discussed its occurrence and isolation in the previous session. In this session, we will discuss that how the structure of Citral can be elucidated. There are different methods which can be used to elucidate the structure of Citral. First of all, when we carry out CHN analysis, we have found that the formula of citral is C10H16O. And we will carry out a series of tests, chemical tests, that are known as chemical methods for the structure elucidation. और उन chemical tests से हम evidences लेते हैं कि structure of citral में कौन कौन से basic features हैं. And the third main step is the spectroscopic evaluation of structure of citral. The first test we can carry out is the bromination test. When you add bromine water, or bromine water is added in such a way you get tetrabromocitral, and this indicates that there are two carbon-carbon double bonds, right? So there are two carbon-carbon double bonds in citral. Further, we don't know the position of the carbon-carbon double bond, whether it is conjugated, isolated, or where it is in the citral structure. Then we carry out its oxidation with potassium permanganate. After carrying out oxidation with potassium permanganate, we got three different products. These one, acetone, levulinic acid, oxalic acid. Then after identification of products and then arrangement of these products, and after keen observation, we can say that there is a carbon-carbon double bond over here. Like this, we come to know that there is a carbon-carbon double bond over here, and there is another carbon-carbon double bond along with the aldehyde. This oxalic acid formation gives a clue that there may be aldehyde in conjugation with a double bond. So after that, we will carry out another oxidation with the ozonolysis. When citral is treated with ozone, we get these three products. This also confirms the presence of two double bonds. One is isolated and one may be in conjugation with the aldehyde. For further confirmation, we carry out another test, that is when citral, it is treated with potassium bisulfate, and we get parakymine. This is parakymine, a product which is obtained by the reaction of this citral with potassium bisulfate. It shows that there must be a joining of two isoprene units, because here are the number of carbons are also the C10, and each isoprene has 5 units. So there must be an evidence. This shows that there must be head to tail connection of the two isoprene units. And when you treat this citral with potassium carbonate and boil it to its boiling point, then what happened? We obtain acetaldehyde along with this type of structure. So formation of these two products also shows that there must be a double bond which is in conjugation with the aldehyde. And when you carry out reduction, you can say that a partial reduction product is also formed like this. It also shows that there must be an aldehyde which is reduced to this one. If you use mild condition, you will end with this type of products, these type of partially reduced products. And if you carry out reduction in a very strong condition, then each and everything is reduced. And the confirmation of presence of aldehyde in conjugation with double bond was also done by the chemical test of citral with sodium bisulfite. When we carry out its reaction with sodium bisulfite, we get mono and bisulfite, both mono and bisulfite. It shows that there must be a conjugated aldehyde. Further confirmation, when you carry out the UV spectral analysis of this one, you can get an lambda maximum, wavelength of maximum absorption at 238 nanometer rather than below 200. So for an isolated double bond, there must be UV, in UV wavelength of maximum absorption below 200. But after 200 and at 238, it shows there must be a conjugation, and that is in the form of conjugated aldehyde. So it is confirmed that their citral has a conjugated aldehyde, that is alpha beta unsaturated aldehyde. Presence of aldehyde can be further confirmed by its reaction with amino alcohol, and when you treat it with amino alcohol, oxime is formed. The formation of this oxime, hydroxylamine, this oxime, it also shows the presence of aldehyde. Upon oxidation with silver oxide, it yields an acid that is geranoic acid. It shows that there is an aldehyde which is oxidized to carboxylic acid. So it further confirmed the presence of aldehyde, and it also confirmed the presence of double bond in conjugation with aldehyde. Upon reduction with sodium amalgam, this is a reducing agent, then partial reduced product is formed. When you start with citral B, you get this one, nerol, and when you start with citral A, then you get with this geraniol, these two isomers of each other. And when you further go for its cyclization, heating and cyclization take place, and you get these type of products. This again confirm the presence of these moieties like this. So you can say that there are chemical methods shows that there is alpha beta unsaturated aldehyde, and double bond, one of the double bond is isolated, and that may be disubstituted like this because oxidation, because of the oxidation product with ozonolysis and potassium permanganate. So we come to know that the two isoprene units, they are joined together by head to tail arrangement connection. So that is the possible structure of the citral. This was further confirmed by spectroscopic methods. IR, its IR shows prominent peak at this one, that is for carbon-carbon double bond, as well as this at 1700, it shows the presence of aldehydes, presence of carbonyl carbons, carbonyl stretching. And here, these are the aliphatic CH stretching, along with it the CH stretching for the aldehyde. So it further confirmed this one. Proton NMR. This is a proton NMR of the structure, and it shows that the presence of aldehyde proton in this region at approximately 10 to 11. It shows the presence of this region at 10, 9 point something, and here this proton at 1.71, it is present in one isomer. In both half the isomer, the proton NMR is the same, and you have double bonded CH 1.71 over here, this one and this one, CH3. This will also you will get this type of spectrum. If you see C13 NMR after two isomers, you will see the difference in this type of carbon. Methyl at this carbon-carbon double bond, it will show 17.0 if it is in one isomer, because if in this isomer, this is citral A, both are you can say opposite to each other. So that is why this is citral A. This carbon is at 17, whereas this carbon is at 23 when it is citral B. So you can differentiate between the two isomers using carbon-13 NMR spectroscopy. Similarly, mass spectrum analysis gives you different peaks. Among this, I have given you some prominent peak like base peak at 69. This is base peak at 69. This shows that the beta cleavage take place, and beta cleavage gives you the peak at 69. And similarly, homolytic alpha cleavage gives you the peak at 29 in this region. Similarly, the molecular weight was found to be 152, which is in accordance with the structure as it was proposed before in chemical methods as well as in proton NMR spectroscopy. The citral is a compound which has alpha beta unsaturated aldehyde, and its one isomer, the double bond, is in cis form, and another isomer it is in trans form. So this is the end of the second lecture.